Right, so we're going to introduce the last of the circuit elements that we're going to deal with, and this is the inductor. So inductors work off of our principle of magnetic induction. So these are going to be devices that will generate an EMF by changing the magnetic flux through the device. Fundamentally, though, what an inductor is it's a device for storing energy in a magnetic field. So where does that magnetic field come from? Well, basically you build an inductor by taking a current-carrying loop of wire and then just wrapping it around. So if you wrap it around something that's iron, right, that'll help strengthen the magnetic field. If you wrap it around something that's not iron, then basically this just acts like it's wrapped around air, and it doesn't act to strengthen the magnetic field. But either way, what I've done is I've created just a series of magnetic loops, or of current-carrying loops that are all lined up. And I know that current-carrying loops generate a magnetic field. And so depending on the way the current is flowing through this wire, I'm either going to have a magnetic field that basically points up or point down, given the way that I've configured this conductor. So what that means is that there's a magnetic field running up and down through the middle of my inductor here. Each loop then receives some magnetic flux from that magnetic field. And then when you start to change that magnetic flux by changing the current, the inductor is going to react to that. Okay? So, but that magnetic field is also where I'm going to store this energy. So we said that inductors will resist changes in the current within a circuit because, again, there's a magnetic field penetrating each of the loops that make up my inductor. And then once you start to change the magnetic flux through each of those loops, that they're going to react by generating an EMF that tries to oppose how you're changing the magnetic flux. So the property that we're going to care about in terms of the sort of the defining property of an inductor is the inductance. And the inductance, so first off it gets the symbol capital L, and it's a measure of the amount of EMF generated for a given amount of change in the current. Let's see how we get there. So for starters, you can define the inductance as the ratio of the magnetic flux through your device divided by the current driven through your device. So the ratio of the magnetic flux to the current will tell you the inductance. And again, I can rewrite this equation so that it says that the magnetic flux is equal to the inductance times the current flowing through the inductor. Well, from Faraday's law, I know that the EMF, and I'm not going to worry about the sign here, so the absolute value of the EMF that I generate when I change the current, or when I change the current in my inductor, is going to be given by the change in the magnetic flux divided by the change in time. And so again, if my magnetic flux is equal to Li, and L is just some property of the inductor, well, it's constant and it pulls out, and so I'm left with L times the change in current over the change in time. So here basically is the equation that gives me the same information that my statement does up here. What the inductance is trying to tell you is it's trying to tell you how much EMF you're going to generate, right? What's the voltage you're going to generate when you change the current. So if you have an inductor that has a large value of its inductance, then you'll get a large EMF for a given change in current. So what are the units of inductance? Well, if you look at this equation, it's going to have units of magnetic flux divided by current. Magnetic flux has units of Webers, current has units of amps, so one way that I could write the units of inductance is Webers per amps. We've given this its own name, it happens to be the Henry. So when you see capital H, in terms of like, hey, a 3.8 Henry inductor, that H is telling you the unit of inductance. All right, so let's come back to again, we said fundamentally what is it that inductors do is that they store energy within a magnetic field. And again, let's start by comparing inductors to capacitors. So how much energy is stored in a capacitor? We said, well, the type of energy stored within a capacitor is electrical potential energy. It's calculated by 1/2 Q times V, and in this case, I'll use my Q equals CV equation to plug in, eliminate V, so I'm left with this expression here that says that the electrical potential energy stored within my capacitor is going to be, there's a factor of 1/2, there's the 1 over the capacitance, right? This just depends on the capacitor. And then there's how much charge you put on the plates. We'll have a very similar equation to calculate how much energy is stored in an inductor. In this case, for an inductor, again, for starters, I know that the type of energy I'm storing is not electrical potential energy, but it's magnetic potential energy. And it's given by, same factor of 1/2. Here I've got the inductance, so rather than 1 over the capacitance, I just have the inductance, but again, that's just a property of the inductor. And then how much current are you driving through the device squared? So a very similar form for calculating the energy stored in the magnetic field in my inductor, 1/2 Li squared. And so this will let us calculate how much energy is in the inductor in the same way that we could calculate how much energy was stored in the capacitor.